remember, let's say a little bit 2 or 3 years ago when you first had our ee-IoT meeting in Oulu. And I think it was a very big growth for me and Hirley. So before you were like, I had a small group starting doing things, and now we're, let's say, already a lot of students and doing a lot of good work. And then I'd like to thank again Constantinos, that's big part of it. And I think he's following us a lot in the project and helping us with some students. And thank you. And it'll be very nice to hear your presentation about portable access points and how this is related to energy efficient. And I think the floor is yours.
Okay, so thank you very much, Pedro. Thank you, Hirley, both of you, for inviting me. Great to be here. As Pedro said, we started this collaboration a couple of years ago. You know, FIREMAN has been I think going very well as a project. It's a bit also a bit of a new area to me as well. And I mean, what I try to do today is to present some tangential results that we've been obtaining in my team that relate to energy efficiency, but not necessarily to are not narrowly constrained, let's say, in the goals of FIREMAN. But hopefully, you know, for the benefit of both projects here, this could be interesting. So, with no further ado, let me share my screen and put up my slides. Give me a second here. Okay, so I guess you can see my slides, right, Pedro?
Yes.
Okay, so my my talk for today is energy efficient technologies for portable access points, and yeah, let me also, I guess you see this as well. So give me a second. Do you see? I want to ask. Do you see just my slides, or do you see also a window with the?
Just the slides.
Just the slides. Okay,
yeah.
So that's very good. Okay, so yeah, the title of my talk is Energy Efficient Technologies for Portable Access Points, and it's work that you know, we've been doing in my research team over the last few years. So especially the part that has to do with the hybrid antenna arrays is work that has been going on for over 10 years now, and several people have contributed to this. But the most recent contributions are with my two PhD students, so Mohammed Haroon Tariq and Nitin. Both of them are doing their PhD in the context of this ITN project called Painless. I'll talk about it briefly soon. And both of them are also registered at Aalborg University. So for their PhD, and you had the keynote by Peter earlier today. So Peter is one of our key collaborators, and he's also one of the supervisors of Nitin. So he's involved in part of the work that I will show. Okay, so an outline of my talk today, I'll introduce a little bit what we call wireless portable access, and more specifically the energy autonomy towards energy neutrality aspect of wireless portable access, and this will be presented in the context of this ITN project that I just mentioned, and then you know, based on this framework, I'll be elaborating on three different directions, three different technology directions that we believe hold some promise in making this kind of wireless access as energy efficient as possible. So one of them is the area of hybrid antenna arrays. Hybrid antenna arrays, as you probably have heard, is a recently emerged topic, and in many ways it's a result of this big push to get what's called massive MIMO in fifth generation wireless networks and beyond. However, massive MIMO, as you probably know, even though it's a technology that has many advantages, comes also with a lot of hardware impairments, hardware constraints rather. So you need many antennas, you need a lot of energy consuming circuitry behind all these antennas. So you have very, let's say, demanding requirements in terms of size and power dissipation and complexity, hardware complexity for this system. So people have been talking about hybrid antenna arrays that use a combination of active elements and either phased phase shifters or parasitic elements, and this part of my talk will be focusing more on the latter. Parasitic antenna arrays is an area of activity in array processing that has been gaining some traction over the last decade or so, and it started with single RF parasitic arrays, but with the emergence of massive MIMO, it's been moving to multi-active, multi-passive arrays. So I'll give a little bit of background on the parasitic coupling aspect, which is something that we have been working on with several collaborators over the last 12 years or so, and which has been leading to becoming now one of the candidate hybrid schemes for hybrid antenna massive MIMO. Then the second technology component I will refer to is related to directional millimeter wave communication. So millimeter wave, as you know, is another important trend that is coming with 5G and for future generations of 5G. It has to do primarily with the fact that we need much more bandwidth, and this bandwidth is, let's say, easily available and accessible in what we call millimeter wave spectrum. So this is, by the way, millimeter wave is a bit of a misnomer. I mean, strictly speaking, it's above 30 gigahertz. People, however, have been using it for any kind of frequencies that are above 60 gigahertz. So in the double digits, let's say 10 gigahertz and above. The focus of the aspect that I will try to illuminate in millimeter wave communication in the context of the portable wireless access that is our focus will have to do with the directional component, and more specifically with some measurements that we made in the 60 gigahertz band with very directive antenna arrays. Okay, so I'll show some results from this measurement campaign. And then the last part of my talk, time permitting, will be related to trajectory optimization for UAV-based wireless access. So this is a part of the PhD of my student Nitin Babu that I mentioned earlier, and joint work with Peter and other colleagues at Alco. Okay, so to set up the stage, some background about this project Painless. So Painless is an ITN project. ITN stands for Innovative Training Network, and as you probably know, those European grants belong to the Marie Curie category, and what they fund is they're collaborative projects that fund individual PhD topics that are all related to fall under a grant scheme, which is the main theme of the project. And in this case, the grant theme of the project is what we call energy neutrality and the portable access point. So we are thinking of wireless access points that are completely wireless in the sense that not only the access segment is wireless, but the backhaul segment is wireless too. This means that you completely eliminate any kind of wires. And of course, the moment you do that, the first, let's say, obstacle that you will meet is that you somehow need to power them as well. So, you know, the typical access point that serves a small cell or the Wi-Fi router that we have at home, it will be usually at least plugged into a power outlet, and it may also be plugged into the fixed the fixed internet jack that we have at home. So we want to take this one step further and say that we'd like to consider access points that are completely detached from any fixed connection. Of course, this has a number of advantages, but at the same time, it's not necessarily needed in all situations. So the situations that call for this kind of wireless access are places where you don't have easy access to a fixed infrastructure. So for example, as you can see on the upper left part of my screen here, in a stadium, or when you have some kind of a special event, or when you have some emergency event, such as in a disaster area, and you want to deploy very fast some kind of a wireless network. This is something that became very apparent even from the days of 9/11. I mean, 9/11 is a disaster that happened while we were still in the second generation wireless networks. And I remember back in those days, because I happened to be in that area, and I was working for Lucent Bell Labs at the time. I mean, Lucent had deployed a team of researchers and wireless engineers who went on the site and tried to pick up signals from second generation phones of people that might have been trapped under the ruins. And the big thing that one of the big shocks that came with 9/11 is that it was very hard to deploy a wireless network on the site of the disaster. So now we are in 5G, and still this remains something to be fully developed. I mean, we do have small cells that have a very, very high capacity. However, deploying those in areas that don't have a fixed grid, either power grid or telecom backhaul grid, still remains a challenge. So for all these reasons, we propose these portable access points, and a portable access point could either be, as shown on the figure here, on a UAV, so it could be hovering over a service area. It could even be, residing on a robot in some kind of indoor area. And it also relates to this, let's say, wireless access on demand, if I can call it like that, concept, which is that, sometimes you can be in an indoor environment and you may not enjoy good coverage from the installed wireless routers in that area. For example, you may be in a basement of a building, and the wireless router may be fixed at some ground level. So you may want to have this little robot that comes to you and gives you access as provider, a bit of such as a robotic butler, let's say, that instead of serving you a drink, serves you wireless access. So all those concepts are behind the project, but the one that is most pertinent to today's presentation has to do with the energy autonomy and energy neutrality. Energy neutrality is an extreme situation where all the energy sources that you utilize for the service provision come from renewables, so you don't burden the environment with extra extra carbon dioxide emissions. But on the way to energy neutrality, in the context of these portable access points, what is really important is energy autonomy. And this means that, if you're going to be serving these emergency or special event areas with those flying access points, those need to have enough battery power to provide the service for a reasonable amount of time, to keep moving their rotors, so to have enough battery to be able to fly and hover, but also to have enough battery to establish the dual connectivity that they need. So to provide access on the wireless segment to a number of users, possibly at very high data rates if those users are streaming video, for example, in the uplink. And also in the backhaul part, they need a very fat pipe, wireless pipe, that will connect them to the fixed point that will carry over the rest of the traffic. So this is the premise of the project. And so we'll get back to that a little later. The whole idea is that the project is leading us to the consideration of new performance metrics that relate not only to the traditional data communication metrics such as communication rate and latency and capacity, aerial spectral efficiency, and so forth, but also to combine that with how much energy you spend to in order to provide this specific data rates, for example. So if to give a simple example, you drain your entire battery in order to provide 1 gigabit per second access, well, that may not be good enough, because then you no longer have battery to keep hovering and keep providing service. So one of the nice aspects of this project is that it defines new performance metrics that combine the energy component and the data communication component. Okay, so as I said, we'll go over those three, let me call them component technologies, that could help these wireless access points reach their goals. Okay, so the first one is hybrid antenna arrays. And as I said, I will focus on those based on mutual coupling. So the starting point for this work, at least from our involvement in this work almost 15 years ago, was this work done in Japan by Gyoda and Ohira back in 2000. And they were calling this a sparse system, so electronically steerable passive array radiators. And so what they had proposed is to form an antenna array that consists of, in this case, those 7 elements that you see on the left part of the slide, of which only one is the active element. So only the central monopole shown in this figure is fed to a proper radio frequency chain, and so we can have full control of its information-bearing signal all the way from the baseband to RF. The other elements, the other 6 monopoles that surround the central monopole, are passive elements, so they're not connected to an active source. They're grounded through an adaptive load, and their role is the following: being placed in the vicinity of the active monopole, they induce mutual coupling due to the fact that they're placed very close to it. So they are positioned, let's say, a fraction of a wavelength away from the central element. For example, lambda over 4 is shown in the upper right part, or even closer than that, lambda over 10, lambda over 20. So when you bring a passive element that is grounded so close to the active one, what will happen is it will induce a secondary current that will run through it, which is due to the electromagnetic coupling with the active one. So even though you only fit the active element, so there's, let's say, one current that is directly controlled by the voltage source that you have, the single voltage source. In doing so, you generate 7 different currents. The one directly generated at your central element, and another 6 currents that are generated in the passive elements through the electromagnetic coupling effect. So, of course, this concept has been known for over a century, and it's the main concept behind this very well-known Yagi antennas that we still use largely around the world for over-the-air TV reception. Because, if you, the concept of the Yagi antennas was that if you have this antenna array with a single active element and many passive ones, you can design the topology and the shape of the passive elements so that the entire array combines the currents that are induced in a constructive way so that it generates a nice beam towards the intended TV tower. Okay, so this is something that has been used for many years, but the big breakthrough that this team in Japan came up with is that they said, look, we no longer have to design this only in a fixed fashion by optimizing the topology of the array, but we can fix the topology and have the adaptive action take place in the control of those loads that ground the passive element. So what they said is, if we have an adaptive way to control the values of these analog loads that ground the passive elements, then we'll be in a position to alter the secondary currents. And if you alter all the secondary currents in a way that is desirable, you will generate a radiation pattern that is desirable. So in some sense, this paper back in 2000 brought together the adaptive filtering community, which used to be largely a baseband processing community, with the antenna electromagnetics community, which was a more analog one. And it said, look, you don't have to do all your signal processing in the baseband domain in order to control an antenna array. You can have a hybrid approach where you only control digitally the active element that you have, and then you control the passive elements in an analog way, but you can compute the loads that are needed in order to generate whatever radiation pattern you want. So in doing so, and let me just go to this slide that shows it a little better. You can construct optimization criteria that control the values for those parasitic element loads such that they generate a certain radiation pattern. And this is an example of what you see here in the center plot. You can see here the radiation pattern of produced by such a single active element antenna array, and this is shown with a dashed red curve, and then you have the blue curve that is the desired radiation pattern. So you have instructed through an adaptive algorithm this antenna array to generate a beam that is as close as possible to a given beam. Why? Because you want, for example, to shape a null in this specific direction. So you can devise algorithms that run adaptively the same way that you were doing this with conventional antenna arrays, where you controlled the baseband weights of all the elements, but in this case, you control jointly the baseband element of the active antenna and the analog loads of the passive ones. And what you see on the left part of this slide is an example of one of those algorithms that we had developed in the paper that you see down here in 2008, that shows you how the algorithm converges to a solution that matches very well the produced beam with the desired one. So now, just to backtrack a little bit and go to this slide, the mechanism through which this is happening as I said earlier, is the electromagnetic coupling, and the electromagnetic coupling can be modeled mathematically the way you see in this slide. So just to make it more, let's say, visually appealing, we're using a simple case of only one active element and two passive ones. And in this case, you have a 3x3 coupling matrix. So this 3x3 matrix is the mutual impedance matrix between the three elements. Again, one of them, the central one, is active, and the surrounding ones are passive. So this is a matrix that is, let's say, given by the topology of your system. And then to this, you add this X component, and the X component is a diagonal matrix that contains the adaptive elements whose values you can control, through which you ground the passive elements. So when you put everything together, you have a relation between the output current vector, so it's the vector consisting of those three currents here, as a function of the input vector, which is basically a vector that contains only the single non-zero voltage source that you have. Okay, so this is the mechanism that neutral coupling takes place, and if you play, and once this mechanism is in place, then you can generate a radiation pattern. The array will generate a radiation pattern, which will be determined by the set of currents you have generated, multiplied by the array response given by the topology of your antenna array. So what the point I'm trying to make here is that this equation here that you see under the within the red box, this is the well-known equation for the far field of an antenna array. It's nothing else but the inner product of the currents induced at the array elements and the array response, which is due to the topology of the array and to the angle of the impinging wave. Now, the difference in the approach we're having here is that the generation of those currents happens through a different mechanism than the one that we have when we have conventional antenna arrays. When we have conventional antenna arrays, those currents are directly controlled by controlling the corresponding voltages of the various elements. When we have neutral coupling, the control mechanism is more involved. It happens through this 3x3 coupling that I showed earlier, and you have to choose. The whole challenge and art here is that you have to choose those parameters XL1 and XL2 so that the induced currents are such that they generate the radiation pattern that you want. So it sounds a little complicated, but in fact, there has been a lot of work that developed several algorithms where you can do that and make the antenna do what you want it to do. And the big benefit in doing so is that you will have much less hardware complexity and a much smaller antenna array, because you will be spared of the extra RF change that would be required if all the antennas were active. Okay, so what you see here in slide 9 are some examples of the beams that this specific single active 2 passive array can generate. In fact, one can prove mathematically that the beam generation capacity of this array can be formulated in terms of an orthonormal basis of a beam space of functions of the beam space domain. And so this B1 of theta that you see here and B2 of theta are the two basis functions that you can combine arbitrarily in order to produce the final radiation pattern, excuse me, of this array. So what you see here as denoted by G of theta is one representative example of a linear combination of those two basis functions. So one can use this mechanism in order to do beamforming with, let's say, lower hardware complexity than the usual. Now, the next step we took in this approach came out of let's say, of a handicap that the original concept had, which is this whole antenna generation, antenna current generation process. The way we're doing it did not depend at all on the channel that resides between the transmitter and the intended receiver. So, which was a problem because, you know, sometimes even though you may want to just shape a desired radiation pattern, well, this radiation pattern could be destroyed by the channel itself. For example, it may have a high gain towards a direction that is blocked due to your propagation. So, as we know from the whole MIMO literature, the optimal way to do things is to take into account the channel if you can. So if the transmitter could know what the channel matrix ahead of it is, then it could optimally produce whatever kind of currents are required in order to reach the intended receiver in an optimal fashion, such as, for example, to maximize the SNR or the SNR in this channel. So this is an approach that was very typical in the MIMO literature, and all pre-coding techniques such as downlink, block diagonalization techniques, and zero forcing, and all of that, and dirty paper coding, they reside on this, they're based on this principle, but nobody had considered that for the parasitic antenna arrays, because the approach we were taking did not allow us to do this. So the work we did here, which was back in 2014, tried to bridge this gap by simply formulating the problem in a slightly different way, which was that we can construct a signal model very similar to what we knew for baseband communications. The only difference being, it's the one that you see here on the top of the slide, the only difference being that now this linear mixing that we used to have between the transmitting antenna array and the receiving antenna array is no longer between the corresponding voltages, but between the corresponding currents on the side of the transmitter and voltages on the side of the receiver. So once you realize that you can write your received vector at the antenna array of the receiver in this way, then you suddenly can involve any parasitic antenna array that you want, because, as I said earlier, the whole challenge in parasitic antenna arrays is how to generate some desired currents. Okay, so by using this formulation here, we can compute with arbitrary precision what is the desired current that we want, and then we can go back to the second problem, which is now how do I find the loads of the parasitic elements that correspond to these generated currents. So this scheme can be described graphically as what you see in slide 12. So we use this current to voltage signal model, and our first step is the one that you see on the lower right part, which is you first compute the desired currents. Okay, for example, you may compute these in order to do water filling or to do some kind of other pre-coding, zero forcing pre-coding. You compute that with arbitrary accuracy, okay, in the digital domain. So you compute this current vector, which is your desired current vector, and then you go to the second step, the one shown on the left lower part here, okay, which is to compute the loads that can generate these currents. And this goes through the mutual coupling matrix that I showed earlier, and that part is less trivial. It involves constraint optimization, and but there's a lot of work that have contributed to solving that problem as well. So once you do that, you can now develop an arbitrary pre-coding scheme using the parasitic antenna array. So that was a bit of a, in our opinion, of a breakthrough, because we didn't know how to use parasitic antenna arrays before for channel-dependent pre-coding schemes. For example, this slide shows a generalized pre-coding matrix. So we can try to construct, to derive rather, this desired current vector as the product of three different components: a pre-coding matrix, a power loading matrix, and our data symbol vector. So with this formulation, you can see more information in the paper below, as well as in other papers. We can do now things that were not possible before. For example, we can do water filling. So what you see in slide 14 is using a very, very simple antenna array of a single active element and a single passive element. So the complexity of this is as much as that of a single antenna device. And with that, we can do coding for a given channel, and you can see that what we receive is very, very close to to what has been transmitted. So we cannot do more advanced things. We can do pre-coding such as interference alignment oriented. So that's something we presented in Globecom that same year, etc., etc. So the idea is that by reformulating the problem in terms of mapping currents to voltages, so transmitted currents to received voltages, this opened a new formulation for utilizing hybrid antenna arrays for any kind of channel-dependent transmission. So we did that only for single active elements, and then with the emergence of massive MIMO, the next step was to pass on to multi-active, multi-passive elements. So I'll show you now a few slides about that. So the idea here is described perhaps best in the figure that you see, the two figures on the right part of slide 17. So, you know, when you have a fully digital antenna array transmitter, you have every antenna linked to an RF unit. Okay, now let's say that you're constrained by the number of RF chains that your device has, your transmitter. So, for example, this is the portable access point that I'm talking about. This portable access point can, let's say, sustain up to 4 RF chains, okay, to be within its main hardware power requirement. And you have those 4 RF chains, but you need an antenna array that has a spatial resolution that is much better than that given by 4 antennas. Okay, so you want to add more elements, but you want to do this without sacrificing all RF chains. Now, our proposed approach for this would be is what is shown on the lower part of the figure, where what we do is for each one of the active elements for a given RF unit, without increasing the number of RF units, we add a number of passive elements around it. So these passive elements around it, what they will do is they will induce those parasitic loads that passive elements, passive currents that I mentioned before, controlled through parasitic elements, and will give us the ability to increase our spatial resolution, produce a beam that is, for example, much narrower, okay, and do so without having to use more RF chains. And the benefit from an energy viewpoint is clear because the RF units are the ones that consume a very big part of our battery power on the portable access point. So this is the approach that we have considered, and yeah, let me I'll probably skip this slide. The slide 19 shows you know, a general how we can get based on this concept a super array structure that combines both active elements and passive elements, and in fact can combine phase shifters as well. So we're not exploiting in the work we're doing currently the phase shifters component that is shown on the right, but we're exploring the parasitic elements through mutual coupling shown in the center. In the more general case, we can have all 3 aspects combined. So we can have fully active elements that are controlled by their individual voltages as shown on the left part of the figure, parasitic elements that are controlled through analog grounded loads as shown in the middle part of the figure, and then phase shifted elements that are controlled by phase shifters as done in conventional phased arrays in the RF domain. So we can have all 3 of these together. Now, we have considered some examples of different topologies where we can do this. One is shown on the top part here. So it's a linear multi-active, multi-passive where we stack the passive elements along the same axis as the active ones. We can do it in a more 3-dimensional design if we have the real estate for that as shown in the bottom, and this of course will give us more opportunities for steering in a 3-dimensional ways. And of course there's many other topologies that one can consider. Okay, and I'll try to skip some of those here just to show you some examples. So as you can see in slide 28, the effect that I spoke about before actually is something that we see in practice. So what you see here is you see three different radiation patterns, okay, produced by antenna arrays that have a varying number of elements. So the one that you see in pink, okay, the magenta color here, this radiation pattern uses a conventional uniform linear array with only 2 active elements. Okay, so it has a beam that is, let's say, a rather wide one that has a 3B beam width that is on the order, let's say, of 100 or 120 degrees. Now, the one that you see in red would be the corresponding radiation pattern that you would have if you had 4 active elements in a conventional arrangement. So it's a uniform linear array of 4 active elements, which though has the price of doubling your hardware complexity. Okay, so the one that you see now in the dashed blue, with the dashed blue line, as you can see, it's very close to the red one, but it only uses 2 active elements. Okay, and how does it do this? Well, it surrounds those 2 active elements by another 8 elements that are passive. These 8 passive elements, they don't cost almost anything, right? They are very close to the active one, so they don't cost extra size. They're lambda over 10 or over 20 fraction of a wavelength apart from the active element. So the entire array actually doesn't really change much in size, and they don't need an RF chain. They only need to be grounded through a very cheap analog load, such as a varactor, for example. Okay, so without really burdening your hardware, you end up having a performance similar to what you would have with twice the hardware. So that's the whole idea, and this is the aspect that of mutual coupling that we want to take advantage of in the hybrid antenna array. So if you think that you're constrained in terms of hardware complexity, you can use the parasitic dimension, okay, to improve the performance of your beam. Okay, you can also say that I will. The hardware complexity, the given hardware complexity, you can improve the performance of the beam, or if you have a given performance of a beam, you can achieve it with much less hardware. So either of the 2 ways is possible. So we have done several different designs for this kind of systems where we can, also steer the beam and control the side lobe levels, etc., etc. Okay. Now, one thing that is though very important when you try to do so is yeah, I see that there is a question. I'll try to answer it at the end if possible. Thank you. An important aspect that comes about when you play with these passive elements is that you need to make sure that the radiation efficiency of your array is also good enough. So not only you produce the desired beam, but you do that in an efficient way. And if you try to solve the problem of calculating the the loads that are required for a given scheme without taking that into account, you may end up with solutions that are very bad in terms of radiation efficiency. So, for example, you create a beam that has a gain of let's say a 10 dBi gain, but then your antenna has a 10% efficiency. So you lose in radiation efficiency what you gain in antenna gain. So that problem is something that we studied recently, and so this is what you see in this slide 34 is the extension of the mutual coupling process that I showed earlier to the case of multi-active, multi-passive elements. So you will see that this vector of voltages here no longer has a single non-zero voltage. It has a number of non-zero voltages that correspond to the active antennas. And so we studied this problem, and what we see, what we derived rather, is a set of conditions, and this was published very recently in the antennas and wireless propagation letters, of IEEE is there's a set of conditions that need to be satisfied for the antenna to radiate. Okay, so those conditions are important because you can now use them as constraints in any adaptive algorithm that you may want to derive in order to obtain the desired, let's say, beamforming properties. Okay, so this these plots that you see here in slide 36 show, you know, some generated beams with, for example, 3 active and 12 passive elements, and you can see that the green radiation patterns are much better than the pink ones. You have a much higher gain with the same number of active chains, but we also do it by respecting the radiation conditions that I showed earlier. So you could be deriving very similar beams to the ones that I'm showing here without taking into account of these conditions, and in that case, you know, the beams would look nice on paper, but your antenna itself would be, you know, wasting a lot of power. Okay, so and as I said, you know, one can use these designs to steer beams or to shape nulls or to shape beams according to what the channel coefficients are, as shown in this animation here in one of the designs that we're using. Okay, now the second part of my talk, and I'm realizing that we're not doing very well with time, is directional millimeter wave communication. This work was done in the context of a project called TIP. So it's a telecom infra project which aims at fixed wireless access, delivering very high gains over the air, very high bit rates over the air on the order of 1 gigabit per second. So we did some work in this project in the part of the channel measurement in millimeter wave frequencies at 60 gigahertz to be specific. So we used these nodes that are provided by the TIP consortium, and these are massive antenna arrays. So you don't see it. This box is the size of, let's say, a wireless router or a laptop, but inside of it, it has close to 300 antenna elements. It has, I think, 288 antenna elements, and it's a hybrid massive millimeter wave array. So it has a number of those elements are active and a number of them are controlled through phase shifters. And the very nice feature about it is that it can generate beams that are on the very narrow, on the order of 2.8 degrees, and it can steer those beams around. So by having these nodes, we could do directional measurements at millimeter wave at 60 gigahertz, and we did quite a few of those measurements. So these are some plots of you know, what kind of angular spread and what kind of delay spread you would see if you place the transmitter and receiver against each other and steer these very narrow beams in different directions. So you can see that in the center you get a very high gain as expected. It's a kind of line of sight situation, and you get very little scattering around. So it's configurations like the ones that you see here on the left lower corner of the slide. And as I said, we did these measurements both in outdoor and indoor settings in order to measure what the channels look like. These are some of the configurations of the measurements. And let me show some. Yeah, so this is a case where we measure from an outside office plaza to the inside of an office that is behind this window here, and we see a channel that varies as shown in the left part of the figure. So the energy is concentrated mostly in the line of sight, but there is a little bit scattering around it. We made many more measurements in such outdoor settings, and you can see here the results also in terms of path loss. So we measure path loss, and then we could fit that to the free space path loss. So the measured ones are the green dots, and you can see that they follow pretty well the free space path loss trend when you're close to the transmitter, and then as you go farther away, you are more consistent with the two-ray model. So there's many more measurements here and results. You can see those in a recent PMRC paper that we presented last August. I'll skip most of these results here, just to show you that we did also some measurements from a moving van and in a suburban environment towards a tower at the premises of the Greek operator Cosmote here in Athens, close to the airport. So these were, we measured here line of sight over a parking lot, in a parking lot situation, and also including some foliage. Again, you can see some of the derived results. So more details, we have CDFs. We also did some indoor measurements. I'll have to skip all the slides and refer to you to the paper for more results. And then the final, in the last remaining few minutes, I want to mention some of the work that Nitin has been doing with Petra as well in trajectory optimization. So, excuse me, he has considered two different problems. The first one is of a single access point, and this is this portable access point that is hovering above a given service area. So it's a line of sight situation. We have a uniform distributed, a uniform density for the intended receivers, receivers, because it's a downlink problem, and we also divide equally the available power to the different users. And what we try to do here is to optimize this metric, this global energy efficiency, which, as I said, is a metric that combines both the your spectral efficiency and your energy efficiency in one. So the definition of this global energy efficiency is shown in this figure, in this slide, and we constructed the joint optimization criteria that try to maximize this global energy efficiency, taking into account both the altitude constraints that we have for the UAV and the minimum data rate constraints that we had for our users. And in doing so, the interesting result is that, you know, there seems to be a sweet spot. So there is an optimal altitude for the UAV that combines in an optimal way both the you know, the energy consumption and the data rate. So that's we believe that's a very insightful and useful result, because it shows you that you know, you can there's a guideline as to how you would deploy a UAV that's providing service you know, in such an emergency or special event scenario, so that it maximizes the use of its battery power and also maximizes the data rate it can provide to the users. We've done similar a similar analysis and optimization for the uplink problem, where now we have multiple UAVs serving the service area, and we have a number of results there, similar constraint optimization criteria, and these are solved through a number of optimization techniques. I won't go much more into detail, just to say that you know, there's a number of algorithms that were developed, and you can check a recent paper in the IEEE Communication Letters for more details. So I think since we're getting close to the 1 hour, I'll summarize here. So our goal is to try to derive techniques that will help the case of energy efficiency, autonomy, and towards energy neutrality, which we believe is going to be a very important aspect for future wireless communication networks. We focus more on the case of portable access points, which we believe present a very promising direction in solving the issue of serving areas that are not well covered by fixed solutions. We consider 3 different technologies that can assist these portable access points, specifically hybrid antenna arrays, directional millimeter wave communication, and trajectory optimization based on joint energy and data rate metrics. And our final statement is that we believe that such technologies and related ones are poised to play an important role for future energy neutral wireless access networks, and we hope to keep contributing in this area and collaborating with any other interested parties that have similar interests. So with that, I would like to thank you all and perhaps open the floor to questions.
Thank you, Constantinos. I think there is a couple of questions in the chat. So can you read the questions? Because
yeah,
I don't know.
Let me stop sharing and let me try to look at the Q&A. Okay, so so there is one. There's three questions here. The first one by Jean de Sousa is: what was the work that your group realized portable access points were becoming a feasible reality from the antenna point of view? So if I understand this, well, the answer to that is it's the opposite approach that we have taken. I mean, we have portable access points as a given, let's say, scenario that we're exploring through the Painless project, and to make that, let's say, more energy efficient, we are introducing hybrid antenna arrays because we know that they will give you a better trade-off of complexity versus performance. Okay, so I hope that's, so is that answering your question? So Arthur, okay. Then the next question is what is to explain about the effect of coupling loss on the beam pattern. Okay, so in fact we don't view the coupling effect as a loss here. We view it as a benefit. So when you have neutral coupling, so this is a question by Reza Ghazalian. When we use parasitic antenna arrays, we take advantage of neutral coupling in order to generate, let's say, a better spatial pattern. So it's no, what was viewed as, let's say, a loss, the fact that some antenna current is leaking, actually power we take advantage of. We want it to leak, that's why we bring the parasitic element very close to the active one, and this leaked power generates a current that we view as useful to the extent that we can control it. And once we can control it, we see, for example, as I showed earlier, that we can get a narrower beam pattern without needing extra RF chain. So Reza, did I answer your question? Okay, I'm not sure if Reza. Yes?
I think I don't know if they can speak in the microphone.
Okay, yeah. Okay, maybe not. So anyway, yeah, please write me back if you want. And then there's a question by Mohammed Shehab. How would the channel estimation of such parasitic antennas affect the energy efficiency of the whole transmission process? Does it depend on the estimation accuracy? So very good question, and thank you. We have two kinds of approaches. One that is channel agnostic. So for the channel agnostic, it's clear that you don't need to know the channel of the transmitter. And as I said, your metric there is how well do you match a desired radiation pattern, and we can do very well in that. Now, in the case where it's channel aware, of course, the channel estimation process will affect it similar to what it would affect a conventional antenna array. So yes, whenever you're going to, if you want to take, let's say, the channel knowledge into consideration, you need to have some decent and reliable channel estimates. Otherwise, you can do more damage than good. So, but this holds for any kind. It's not particular to the parasitic antenna aspect. I mean, anytime you want to make a technique better by taking into account some extra information such as channel knowledge here, this information needs to be good enough. Okay, if it's poor, you'll end up doing more damage than good. So your point is well taken, and of course, estimation accuracy will affect a lot the performance, and it will affect everything, the energy efficiency and your communication rate. Okay, so that's quite clear.
Thank you, Constantinos.
You're welcome, Mohammed. And let me see if there's another one. Oh, and then Onel. Hi, Onel. So Onel is asking, is it possible to estimate the efficiency of the channel matrix for such parasitic arrays with a single active element? Do you require estimating the complete channel matrix? So the answer, part of the answer is what I said before. If we need to estimate it, yes, we'll have to devise a channel estimation process, and that's similar to any training-based channel estimation process that you would have in conventional arrays. So yes, we can do this, but to the second part, do you require to estimate the complete channel matrix? The answer is no. This depends on what kind of approach you take. So if you take a channel-aware approach, yes, you would have to do so. I mean, channel matrix, when you have MAMP, it's a single, it's a vector matrix if you have MISO. Okay, but you can also have open loop techniques where you don't need the channel at all. Okay, so Onel, I'm not sure if I answered.
Thank you very much.
Okay, you're welcome. And that's about what I see in the chat.
So yeah, I think there is other questions, but then I think you can answer later. There is some questions in the
Okay.
chat, but because we are like run out of time, I think you can continue. And then thank you very much again, Constantino. It's always a pleasure to hear your lectures,
Yeah.
and hopefully you can organize more next year. So
yes, thank you very much, Pedro. And
very
great
nice
being
to
here.
hear.